Welcome back. In our first class, we introduced ourselves to the concept of number system. So we have trying to introduce a number called the natural number, whose set of elements is 1, 2, 3, dot to infinity, the positive infinity. Okay, and then we have also tried to introduce another set of number called the whole numbers. Okay, we start from 0, 1, 2, 3, dot. Okay, also going to uh, positive infinity. Okay, and we have been able to show the relationship between these two numbers. Okay, and one of such discussion is that the set of natural number is a subset of the uh, set of the whole numbers, and we have said that whole numbers, this set of whole numbers, okay, is simply the union of the natural number and the set of 1.0. Okay, so one thing we like to look at on these whole numbers is some of the subclasses of number that one can get from here. These subclasses are very useful both in its theoretical use and application uh, use. Okay, these subclasses of numbers that we are talking about here, okay, there are some of the known numbers that we are used to. The first among them is the first two numbers that we have here. Okay, so the first two number, okay, is what referred to as the binary numbers. Okay, and these are the set of this is a set of 0 and 1. Okay, okay, this is one of the subset of this number is 0 and 1, though this is infinite and you can say this is finite. Okay, so it's one of the subsets. Okay, we can get this by taking this first two number and delete the number from 2 upward. Okay, this is binary number, and for some of us who are used to the binary systems, okay, these are the number we mostly discuss there. Okay, so another type of number that we have in this set is what referred to as the prime numbers. Prime numbers, that is after the first two binary, the number 2, 3, 5, 7, 11, and so on, up to positive infinity. And before now, the definition of a prime number is that the number which is positive, that is one. A prime number is always positive, and it is only divisible by one and itself. Any number that is positive and it is divisible by one and itself is called a prime number. Okay, so you will see that this set of elements that we have here possesses what we have just said. For example, since number 2 is the first prime number that we know, 2 can only divide itself and 1. Okay, another definition, okay, for better understanding, is that a prime number is a number that is positive and cannot be broken down into two lesser numbers, two lesser multiplicative number. Okay, if you look at these two, okay, let's first of all use the first definition. 2 is divisible by 2 and 1. That is taken. 3 is only divisible by 3 and 1. 5 is only divisible by 5 and 1. Okay, and if you look at all this number, okay, we can't break any of this number down into two multiplication number, okay, different from 1. Okay, 2 is only 2. Okay, there is no number you can break 2 into in such a way that you have 2. No such number. The same thing happens to 3. You can't break 3 down to 2 numbers in such a way that when you multiply those 2 numbers, you have 3. 5 also has that attributes. 7 also has that. You can't break all these numbers down into 2 numbers in such a way that one can have such a number back. Okay, so these are the number we refer to as the prime numbers. Okay, in the number theory, okay, this type of numbers, okay, one can study extensively, okay, the kind of structures and both theoretical and applications of this number. Okay, I've been studying that area. Okay, so the next number we can think of among this number is what we refer to as the composite numbers. This composite number is somewhat the opposite of the prime numbers. In fact, when we say composite number are any number that is not a prime number. Okay, if you look at it, it means after the omission of this prime, the remaining numbers such as 4, 6, 8, 9, 10, okay, up to the positive infinity are what referred to as the composite numbers. Okay, just as we have said earlier here that the prime numbers cannot be broken down into 2 numbers or 2 multiplicative numbers. Okay, so this does not, or this cannot be broken down into 2 multiplicative number, but this does. Okay, in fact, this composite number can be broken down into at least 2 multiplicative number, and those numbers are usually prime. Okay, let's take for example this number 4 can be broken down into 2 multiplicative numbers, and that will be 2 times 2. Okay, where 2 is a prime number, and okay, of course 2. Okay, this can also be broken down into 2 prime number, 2 multiplicative number called the prime numbers, and that's what 2 times 3. This can also be broken down into 3. Of course, we say at least 2 multiplicative number. Okay, so here we have 2 times 2 times 2. Okay, as you can see, they are all prime. This can also do the same. 3 times 3, prime. Okay, we can also have 2 prime here, which is 1, 5. Okay, the next one here is the number 12. And the number 12 can have 2 times 2 times 3. Okay, 2 a prime times 2 a prime, then times 3 a prime. Okay, and so on and so forth. So these are what we refer to as the composite numbers. Okay, so anytime we think of the set of whole numbers, okay, along with that, we can also think about these 3 subclasses, okay, that are embedded in it. Okay, so just like we said that these prime numbers are useful both in for theoretical purposes and application. Okay, same thing for the composite numbers. Okay, they are all useful in applications. Okay, let us now extend the notion of uh, whole numbers to set of integer numbers. So let's do that now. So the set of integer numbers is defined as z. As we have said, this symbol z is a symbol for integer numbers, and we have said it means whole number. Okay, in the German word. Okay, and so this is a set of numbers. Okay, from negative. Okay, that is from negative large number. Okay, that is integer. Okay, up to -3, -2, -1, 0, 1, 2, 3. Okay, so and so on to positive uh, large number there. Okay, so we can look at these integer numbers as the set of three numbers. Okay, so the first being negative, at the middle we have just one number 0, and here we have a number positive. Okay, or we can group them into two by say if we with the inclusion of 0 here, we can call the entire this a whole number, just like we have said earlier. Okay, that the entire this is whole numbers. Okay, so with the introduction of negative numbers to this set, okay, we can have a property of this set. Okay, and as we will see, this property, this set of numbers has more properties or attributes than the natural number or numbers. Okay, so this is so because of the introduction of the negative integer numbers. Okay, so let's take them one after the other, and then but before that, let's quickly make a remark that from our explanation here. So when we see that the set of natural number, of course, we have said earlier that this is a subset of the whole numbers, and this whole number is a subset of the integer numbers. Okay, so this is very key. Okay, this is very key. Okay, so that's our observation. Okay, the entire number here. Okay, in these two sets. Okay, is contained in the integer numbers. Okay, so that is obvious from the definition here. So let's look at the properties of the integer numbers. Okay, so we'll now make this more elaborate. So properties. So we'll call this Z1. Okay, to make the first properties of the integer numbers. Okay, so here we'll say let A comma B belongs to Z, then A plus B is an integer number. Okay, if you pick any two numbers in a set of integer numbers, okay, so the addition of the two numbers is also an integer number. So as we have said earlier, for the properties of natural number, this means a closure property under addition. So property 2. Okay, so because of the introduction of the negative integer numbers, okay, so when we observe that subtraction rules for this, okay, if you pick any two numbers in the set of integer numbers like this, when we perform this operation is always an integer number. Okay, so 3. Then we'll go for multiplication. So if you consider any two numbers there, okay, so this operation also holds, and it is called an integer number. 8 multiplied by b is an integer number. Okay, so this means this is also closed under multiplication. Okay, so but we will observe that division can't hold there. This is because if you pick any two number where this denominator is not 0, this is not an integer number. Okay, it suffices for us to pick any two numbers. Let's say the number 2 and the number 3, for example. Okay, this type of number is 0.6666. Okay, we can't find this type of number in this set. Okay, this does not mean that because there are some number that will pick here that will give us an integer. Okay, but for the fact that there are at least some numbers which are not here, okay, will not make this to be satisfied, since we have some numbers which are not in the set. Okay, so division can hold there, and then it cannot be included. Okay, so the property 4 is the order structure. Okay, that is, if you okay, let's make it more elaborate. Now for any A, B in Z, okay, either this happens, okay, so we may like to include one possibility, that is, that's the possibility of the two number I pick are the same. Okay, so since the selection has to be random, okay, so there is a possibility that the two numbers are the same. Okay, so these are the 4 basic properties under the integer numbers. Okay, so as we have said earlier, for the natural numbers, one can make more one can introduce more sub properties under each of these. Okay, where we'll classify both addition and subtraction into the same class. Okay, this is another class, this is into another class. Okay, so let us look at this in details. Okay, firstly, under this property, we have addition, so we'll regard this as the same here. So we have addition, multiplication, and order. Okay, and if you compare these properties to that of natural number, okay, we'll see that this property 2 here is not in the set of the natural numbers, and this, of course, make this the set of integers a larger system than the natural number. Just like we have remarked that set of natural numbers is only contained in the set of integer numbers. Okay, this is because of this property, these singular properties. Okay, so let's now make in each of these property, okay, more more attributes. Let's discuss more attributes on that there. Okay, so this time we'll try to tabulate in order to see some of the features here. Okay, so let's tabulate. Okay, so let's make this table. Okay, we'll call this addition. That is, all the operation we perform here were based on addition. all the operation we'll be talking about will be based on multiplication, and all the operation we'll be talking about based on the other properties. Okay, as we have said, the that of the subtraction is embedded here. Okay, so there is no so let's look at this one after the other, just like we have said in the main property. Okay, so here, if we have two elements, I mean closure property, that's why I've applied that. If A, B are integer numbers, okay, A plus B is an integer. That is what we have said in the first property, that A plus the addition of two integer numbers is an integer. Okay, that is, it is closed under the addition. Okay, same thing also holds here. If A and B, okay, are integer numbers, okay, then A dot B, or A multiplied by B, is an integer. Okay, so that is for this. Also under the order, if A is less than B, okay, there exists a number, let's call it P, is Z, such that uh, A plus P is less than B plus P. Okay, so that is valid under the addition. Okay, what you are saying is that if you have two numbers such that one of them is lesser than the other, okay, if we pick any number P in this set of integers, okay, this holds. Okay, and for the this is for the addition case. As for the multiplication, okay, such a P cannot be any P in Z. Okay, such a P, okay, must belongs to the positive integer part of this. Okay, and before we can see that this preserve the multiplication under the other. Okay, so this is what we are trying to do, that if A is less than B, this order can be preserved, okay, when we perform addition. So if you introduce a number P, okay, you can see that it is preserved for any P, okay, we'll pick. Okay, and we have said for the multiplication, okay, we cannot pick any P except for the positive B. That's when the order can be preserved. Okay, I think this is taken. Okay, and this is under the, of course, by the virtue of this, A plus P, okay, is an integer. B plus P is also an integer. Also by the virtue of this, A dot P is an integer, and P dot P is also an integer. Okay, so that of the closure property is taken. Okay, so another thing we want to look at here is the commutativity. So let's read this line. Commutativity. Okay, so let's put hyphen here to show that this continues there. Okay, so here again, if you have A, B to be integer numbers, then A plus B is equal to B plus A. Okay, so this is what we refer to as commutativity. That is, if you reverse A and B, okay, if A is plus B here, and when you reverse it as B plus A, okay, these are the same. Okay, they are the same. And the same thing happens for multiplication. It is commutative under multiplication. This for addition, multiplication. And of course, if the same thing happens there, okay, so it is obvious there anyway. Okay, since we have said if the order so we have the same order for the two. Okay, these two are the same if this happens. Okay, so let's take another one. That is the associativity property. Associativity under addition. For the I think for the other, okay, what we have said there is okay, okay. So associativity. So let's give a clearer picture of this so that one can make a meaningful remark. Associativity. Okay, so here is for addition and here is for multiplication. For addition, then for multiplication. Okay, again, if you have three integers, for integers a, b, and c, okay, addition of these two numbers, okay, plus c, okay, is the same thing as addition of this plus this, okay. Okay, this statement is true under addition, and we call that associativity under uh, the integer number. Okay, so the same thing if you have three integers a, b, and c. Okay, so this statement is also true. This is also true under this. Okay, and in both cases, okay, we call this associativity under addition, associativity under the multiplication. Okay, so let's take another one. Okay, so this one combines both addition and multiplication. So let me create a kind of a combined table here. Okay, so we'll call this distributive or distributivity. Okay, so also if you have three number for integers a, b, and c, okay, a dot b plus c is the same thing as this. Okay, this odd, or if we have in other way around, if what you have here is two okay, if you write it in another way, this actually holds. Okay, as you can see, this combined both the addition and multiplication, and it is being referred to as the distributive law. Okay, so now let's look at the identity law. Identity law under the integer numbers. Okay, what this means is that for under the addition, when you pick a number and that number is added to another number, if your result is the number that you introduce, okay, in such a case, this number will be called identity. Okay, if for any a, when I add a to a number and I have the same a, okay, in such a case we will refer to as this zero as identity. Okay, because this has made me reproduce a even after the addition. So in this case, this is zero is identity. Okay, so here we have zero identity under the addition, and for this can only happen, we can only produce a under multiplication if the identity is 1a. Okay, so this is how we introduce the identity. Okay, there is one more property or two. So okay, we'll call this the inverse law. The inverse law. Okay, that is if you have a number, okay, and the opposite of this number is added to this number, okay. The number 0, as you can see, the number 0 is part of the integer number. So this odd and this negative a is called, for under the addition, okay, when you add a number with with its inverse, okay, we have the identity, okay. As you can see, the identity here is a 1. So if you have a number, okay, and what we want to multiply the number with its inverse, this will, all the inverse will come here, and of course this will make it 1. Okay, so the only number that can satisfy this is two numbers, okay, and the the only a is either a equal to 1 or a equal to -1. Okay, so if you pick any number other than these two numbers, okay, this will not hold. Okay, but if it is 1, okay, for example, this will always hold. Okay, so here we'll mark that the only invertible numbers here is 1. Okay, so if you pick 1 here and you take the inverse, this is so because this element is not allowed, okay, under the integer numbers. For example, if I pick 2, for example, a is 2, here 2 raised to the power -1 is 1/2. This number 1/2 is not an integer number, and such you can't use it, okay, to define the inverse law. Okay, but in the case where we pick it to be 1, if this a is 1, okay, this will be 1 multiplied by 1 raised to the power of -1, which is also 1, okay, and we multiply that, we have 1. Okay, so any number other than these two numbers, okay, cannot hold under the inverse law of integer numbers, okay. Or let us make it clear, the only invertible numbers in this place is 1 or -1, okay. So to close this chapter, let us also introduce one more property, okay, one of the very key property here too, okay. And this property does not hold for the addition, it's only hold for the multiplication. And let us state that, okay, must not leave this place without stating that law, okay. No zero divisor. This is very important. No zero divisor. Okay, we do not have for the addition. The addition was not also about, if you have two numbers like this equation is possible under the integer numbers. But if it happens, okay, that a dot b is 0, where a is an integer number and b is an integer number, okay, so this means either a is 0 or b is 0, okay. And this is so because zero divisor is not allowed there, okay, because we can't find a number 0/0 under the integer numbers. We do not have such a number. In fact, 0/0 is actually not a number when it comes to a number system. 0/0 is not a number. And if such case happens there, it either means this is 0, okay, no, if this is 0, 0 multiplied by b will give us 0. And if b is 0, okay, and this is not, when multiply, okay, we'll still have that, okay. And in some of our this make me remind the concept we use under the quadratic equation, when we are finding the root of a quadratic equation. And then when I arrive at something like this, where you have two factors multiplying one another and they are equal to 0, okay. So here is the law that we use, that either the first factor is 0 or the second factor is 0. So if the first factor is 0, okay, that will help us to get the the first root of the equation, and if the second factor is 0, okay, that will help us again to get the second root of the quadratic equation. Okay, so this is that on the integer numbers. Okay, there are more things there, okay, but we are trying to explain to ourselves, okay, some of the basic properties or attributes of integer numbers. Okay, so this is where we'll stop for this, and when next we come, we would like to look at another concept of a under the number system, and this time we'll call this number the rational type of numbers. Okay, that is number where decimal is allowed. Okay, that is combination of the integers and the decimal numbers. Okay, integer and non-integer numbers. Okay, so this is where we'll stop.